This one says find the derivative using the limit definition. Our definition for the derivative is f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And we're going to do this for the function f of x equals 2x minus 3. I'm going to follow the limit definition for the derivative, and I want to write out f of x plus delta x, and that means everywhere I see an x, I want to change it to x plus delta x. This is 2 times x plus delta x minus 3. Then I want to subtract f of x. Subtract 2x minus 3, and I want to make sure I put parentheses around 2x minus 3 to subtract the whole thing, and I want to divide by delta x. So I just noticed that I left off the limit, so I'm going to erase this, add the limit as delta x approaches 0, and this is our derivative. So I'm going to do some simplifying. This is going to be the limit as delta x approaches 0, and the simplifying is that I'm going to use the distributive property here and the distributive property here. This gives me 2x plus 2 delta x minus 3 minus 2x plus 3 all over delta x. I've got some terms that'll cancel each other out. I have a plus 2x and a minus 2x, a minus 3 and a plus 3. So I'm going to be left with the limit as delta x approaches 0 of 2 delta x over delta x. The delta x's reduce or cancel out, and now I have the limit as delta x approaches 0 of 2. The limit of a constant is that constant. So I'm going to calculate or prove the formula for the derivative of cosecant. And what we would do is rewrite the cosecant in terms of sines and cosines. And using the reciprocal identities, cosecant is the same thing as 1 over sine. So I'm going to use the quotient rule to be able to calculate this derivative. So using the quotient rule, let me give you guys the quotient rule. That's when you have a fraction that you're trying to take the derivative of. And the way you calculate the derivative when you have a fraction is to take the denominator and multiply it by the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So I'm going to do that with a numerator of 1 and a denominator of sine x. So using the quotient rule, I would do the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. So I have sine x, the derivative of 1 is 0, and the derivative of sine is cosine. Sine x is cosine x. And in the bottom I have sine x squared or sine squared x. So this gives me negative cosine x over sine squared x. So this is a little bit complicated, so I'd like to use some trig identities to simplify it. So I could write this as cosine x over sine x times 1 over sine x. And cosine x over sine x is the same thing as cotangent. That's our quotient identity. And 1 over sine x is cosecant x. So we have the derivative of cosecant x being negative cotangent x times cosecant x. So in this question, we want to find the one-sided limit, the limit as x approaches 2 with a minus, that's the limit to below. The limit as x approaches 2 from below of f of x, and f of x is this piecewise defined function. This piecewise defined function is 3x minus 5 whenever x is less than or equal to 2, and 0.5 x squared when x is greater than 2. So you can see that the value of the limit that we're approaching 2 is the same place where these pieces are joined together. So what we want to pay attention to is that our limit is approaching 2 from below, and that means less than 2. So we want to go over here and use the equation that represents the same thing, x being less than or equal to 2. So we'll find that limit by doing direct substitution right into that equation. 3 times 2 minus 5, that's 6 minus 5, which is 1. So our limit as x approaches 2 from below of f of x equals 1. So we want to find the limit as x approaches negative 2 of the greatest integer less than or equal to x. So this double brackets here is representing the greatest integer less than or equal to 2. So what I know about this function is that we have discontinuities at every integer. The graph sort of looks like a floating staircase. And so at every integer, on one side, the limit will approach one number, but on the other side, the limit will approach a different number. So I have to be very careful about finding the limit of this. And we want to focus on finding the one-sided limits first. So I'm going to find the plus, and then we'll find the minus. So let's focus on finding the limit as x approaches negative 2 from above. That's what the plus means. And so I'm going to do kind of a slight modification of direct substitution. And the modification that I'm going to do is, instead of choosing this exact number, I'm going to choose a number that's a little bit bigger than negative 2. So if I'm thinking about my number line, I've got 0, negative 1, and negative 2. To be a little bit bigger than negative 2 would be on this side, the right side of 2, and that looks like a number that's maybe like negative 1.5. So if I use direct substitution with negative 1.5, the greatest integer that is less than or equal to negative 1.5, so if my number is right here, the greatest integer that is less than that would be negative 2. Then when I'm trying to find the other one-sided limit, which is negative 2 from below, I'm going to do the same thing and make sure I pick a number that is a little bit smaller than negative 2 to substitute. That'd be something like negative 2.5. And if I use direct substitution, the greatest integer less than or equal to negative 2.5 would be a negative 3, because less than is on the left when you're looking at the number line. So this limit would be negative 3. And then when you're looking at the overall limit, the limit as x approaches negative 2 of the greatest integer function, we can see that the one-sided limits are approaching different values, so this overall limit does not exist.